Hello, welcome to Infinite Science. In this video, we're diving deep into the Milky Way, the massive spiral galaxy we call home. A structure so vast that light takes 100,000 years to cross it, yet we've never seen it from the outside. We'll explore its hidden structures, its violent past, its invisible components, and the mysteries that still baffle astronomers today. Everything you've ever known exists inside a structure we've never seen from the outside. Every person who has ever lived, every civilization that rose and fell, every thought, every dream, every moment of human history, all of it happened inside a cosmic island we call the Milky Way. But here's the unsettling part. We live inside this galaxy, embedded deep within its structure, and because of that, we barely understand it at all. Imagine trying to map an entire continent while standing in the middle of a dense forest, unable to see more than a few trees in any direction. Now imagine that forest is not just around you, but above you, below you, stretching in every direction for distances so vast that light itself takes thousands of years to cross them. That's humanity's view of the Milky Way. We're cartographers trapped inside the very thing we're trying to chart, surrounded by obstacles that hide the bigger picture. And what we have discovered is stranger than anyone imagined. We've found that most of our galaxy is invisible, that we're moving through space at speeds that would seem impossible, that the Milky Way is a cannibal, consuming smaller galaxies and growing larger over billions of years, that our home is held together by something we can't see, can't touch, and don't understand. The Milky Way is not just our cosmic address. It's a mystery we're living inside, trying to solve from the inside out. And every answer we find raises a dozen new questions. The Milky Way is a barred spiral galaxy, a cosmic pinwheel of stars, gas, dust, and mysteries we're only beginning to unravel. But let's put some numbers to this impossible structure, keeping in mind that many of these numbers are estimates, approximations, educated guesses based on limited observations of something we can never fully see. The Milky Way contains somewhere between 100 and 400 billion stars. We don't know the exact number. We can't count them. We'll never count them. Many are hidden behind vast clouds of dust. Others are too dim to detect with even our most powerful telescopes. Some are so distant that their light hasn't had time to reach us yet. Others have already died, but their light continues traveling through space, making them appear alive when they're already gone. Some estimates push the number even higher, perhaps 600 billion stars. The uncertainty itself tells you something about the scale we're dealing with. We're trying to count objects in a structure so large that light takes 100,000 years to cross it, using instruments that can barely see a fraction of what's out there. And stars are just the beginning. Each of those stars could host planets. Conservative estimates suggest there are at least 100 billion planets in our galaxy. Others argue the number could exceed 1 trillion. Rocky worlds like Earth, gas giants like Jupiter, ice planets circling dying stars in the outer reaches of the galaxy, ocean worlds covered entirely in liquid water, locked in perpetual darkness beneath kilometers of ice, desert planets scorched by binary suns, rogue planets ejected from their solar systems, wandering alone through interstellar space. Most of them we'll never see. Most of them we'll never even know exist. They're too far away, too small, too dim to detect. They orbit stars we haven't discovered, in regions of the galaxy we haven't mapped. The galaxy stretches roughly 100,000 light-years across its main disk, though some observations suggest it might be even larger, perhaps 120,000 or 150,000 light-years depending on where you draw the boundary. To put that in perspective, light, traveling at 300,000 kilometers per second, fast enough to circle Earth 7 times in 1 second, takes 100,000 years to cross from one edge of the galaxy to the other. If you could somehow travel at the speed of light, which you can't because the laws of physics forbid it, it would take you a 100 millennia just to traverse the width of our galaxy. That's longer than all of recorded human history, longer than humans have existed as a species, longer than our ancestors have been making stone tools. The Milky Way's mass is estimated between 1 and 1.5 trillion times the mass of our Sun. Some estimates go as high as 2 trillion solar masses. But here's where it gets strange. Most of that mass isn't stars. It isn't gas or dust or planets. It's something else entirely. Something invisible. Something we can only detect through its gravitational effects on the things we can see. We'll come back to that. Because the invisible part of the galaxy is the most important part, and the least understood. The disk of the Milky Way is relatively thin compared to its width, only about 1,000 light-years thick in most places, though it thickens near the center and thins toward the edges. Picture a dinner plate, and you'll have a decent mental model of the galaxy's proportions. But this isn't a static disk. It's not a rigid structure. It's more like a fluid, constantly flowing, rotating, evolving. The entire disk rotates around the galactic center, but not like a solid wheel. Different parts rotate at different speeds. Stars closer to the center complete their orbits faster than stars farther out, though not as much faster as they should, which is one of the clues that led astronomers to discover dark matter. And we're inside it, spinning along with everything else, unable to step back and see the whole picture. The Milky Way also has a central bulge, a roughly spherical concentration of stars at the galaxy's core, extending about 10,000 light-years from the center. This bulge contains some of the oldest stars in the galaxy, formed billions of years ago when the Milky Way was young. These stars orbit in random directions, not following the ordered rotation of the disk. Cutting through the bulge is a bar, an elongated structure of stars about 27,000 light-years long, though estimates vary. This bar rotates as a unit, like the handle of a spinning wheel, and it plays a crucial role in funneling gas toward the galactic center, feeding star formation and possibly feeding the supermassive black hole that lurks at the galaxy's heart. Not all spiral galaxies have bars. Some are grand design spirals with perfect arms and no central bar. The Milky Way is a barred spiral, which means its structure is influenced by this central bar in ways we're still working to understand. And beyond the visible disk, beyond the stars and gas we can see, there's something else, something much larger. The dark matter halo. This halo extends far beyond the visible galaxy, perhaps 500,000 light-years from the center, perhaps more. It's roughly spherical, not disk-shaped like the visible galaxy, and it contains the majority of the Milky Way's mass.
But we can't see it. We can only infer its existence from the way stars and gas move, from the gravitational effects it produces on visible matter.
The Milky Way you see in images, the beautiful spiral of stars and nebulae glowing against the darkness of space, is just the tip of the iceberg, the luminous part, the part that emits light. Most of the galaxy is dark. If you could step outside the Milky Way and look at it from above, impossible, but imagine, you'd see a beautiful spiral structure, a bright central bulge glowing with the light of billions of ancient stars packed tightly together. A bar of stars cutting through the core, slightly tilted relative to your line of sight. And sweeping outward from that bar, several spiral arms, each one a river of stars and stellar nurseries flowing through space in graceful curves. You'd see the Perseus arm stretching along the outer edge of the galaxy, the Scutum Centaurus arm, one of the galaxy's major features, sweeping through the inner disk, the Sagittarius arm, closer to the center, and smaller structures, spurs and branches, connecting the major arms, creating a complex web of stellar density. But we can't see any of this directly, not from where we are. From Earth, when we look toward the galactic center, we're peering through 26,000 light-years of stars, gas, and, crucially, dust. Cosmic dust made of tiny particles, carbon grains, silicates, ice crystals, complex organic molecules. Each particle is smaller than the width of a human hair, smaller than a grain of sand, sometimes as small as a large molecule. But when you have trillions upon trillions upon trillions of these particles scattered across interstellar space, they block visible light almost completely. It's like trying to see through fog. No matter how powerful your telescope, if you're looking in visible light, the galaxy's core remains hidden behind a veil of dust. This is why, for most of human history, we didn't know we lived in a spiral galaxy. Ancient astronomers saw the Milky Way as a band of light across the sky, but they had no idea what it was. Some thought it was a river of milk spilled by the gods. That's where the name comes from. Others thought it was a seam in the celestial sphere. Still others thought it might be the glow of countless distant stars, but they couldn't prove it. It wasn't until the early 20th century that astronomers began to understand the true nature of the Milky Way. And it wasn't until the 1950s and 60s, with the advent of radio astronomy, that we could start mapping the galaxy's structure by observing wavelengths of light that pass through dust unimpeded. At the very heart of the Milky Way lies something extraordinary, a supermassive black hole called Sagittarius A star, often written as SGR-A. This black hole contains approximately 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. To put that in perspective, Mercury orbits the Sun at a distance of about 58 million kilometers. Sagittarius A has 4 million times the Sun's mass, squeezed into a space smaller than that orbit. The black hole itself, the event horizon, the point of no return, is only about 24 million kilometers across, smaller than the distance between Earth and Venus. It doesn't emit light. Nothing escapes a black hole, not even light itself. But we can see its effects. Stars near the galactic center orbit this invisible monster at tremendous speeds. One star, designated S2, orbits Sagittarius A once every 16 years, reaching speeds of up to 7,600 kilometers per second, about 2.5% the speed of light at its closest approach. Astronomers have been tracking S2 and other stars near the galactic center for decades, watching them zip around an invisible point in space, their orbits perfectly explained by the presence of a 4 million solar mass black hole. It's one of the strongest pieces of evidence we have for the existence of supermassive black holes. In May 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A, or rather, the glowing ring of superheated material swirling around it. The image showed a fuzzy orange ring with a dark center, the shadow of the black hole, the region where light is bent so severely by gravity that it can never escape. The image took years to produce. It required combining data from radio telescopes across Earth, in Hawaii, Arizona, Spain, Chile, Mexico, Antarctica, and other locations, turning our entire planet into a single massive observatory with a resolution equivalent to seeing a donut on the moon. But even this wasn't a direct observation. We're seeing the shadow, the outline, the gravitational distortion caused by something we still can't directly observe. The black hole itself remains invisible, hidden behind its event horizon, its interior forever inaccessible to observation or measurement. And Sagittarius A isn't alone. Surrounding it, within the innermost few light-years of the galaxy, is a dense cluster of millions of stars, many of them massive and short-lived. These stars orbit in a chaotic swarm, their paths influenced not just by the black hole, but by their gravitational interactions with each other. The spiral arms of the Milky Way are where most of the action happens. These aren't solid structures, they're density waves, regions where stars and gas bunch together temporarily before dispersing again. Think of them like traffic jams on a cosmic highway. Cars come and go, but the jam persists, always in the same location, always slowing traffic. In the case of spiral arms, stars and gas clouds enter the density wave, slow down due to increased gravitational pull, then speed up again as they exit the other side. The arm itself doesn't rotate as fast as the stars. It's a pattern that persists even as individual stars move through it. Inside these spiral arms, vast molecular clouds collapse under their own gravity, forming new stars. Some of these stellar nurseries are so enormous they dwarf anything in our local neighborhood. The Carina Nebula, visible from Earth's southern hemisphere, is a star-forming region about 7,500 light-years away. It spans roughly 300 light-years across and contains thousands of young stars, some of them more than 100 times the mass of the Sun. The radiation from these massive stars is so intense, it's sculpting the surrounding gas and dust into towering pillars and strange shapes, visible in stunning detail in images from the Hubble Space Telescope and James Webb Space Telescope. The Orion Nebula, closer to us at about 1,340 light-years, is actively birthing new solar systems right now. Deep within the nebula, hidden behind thick clouds of dust, hundreds of young stars are surrounded by protoplanetary disks, swirling clouds of gas and dust that will eventually coalesce into planets. In a few million years, the Orion Nebula will be a cluster of mature solar systems, each potentially hosting rocky planets, gas giants, and all the other components we see in our own solar system. The Eagle Nebula, made famous by the Hubble Space Telescope's Pillars of Creation image, is another stellar nursery about 7,000 light-years away. The pillars themselves are columns of gas and dust several light-years tall, where new stars are forming inside dense clumps. These pillars are being eroded by radiation from nearby massive stars, slowly evaporating into space, but not before giving birth to new generations of stars.
We can see these regions because they glow. Young, massive stars heat the surrounding gas until it radiates light in visible wavelengths. The characteristic red glow of many nebulae comes from hydrogen gas excited by stellar radiation. But this visible light shows us only a fraction of what's happening. Most of the star formation is hidden behind dust, visible only to infrared telescopes that can peer through the obscuring material.
And most of the galaxy's structure remains invisible to our eyes, hidden either by dust or by sheer distance. Surrounding the visible disk is something even more mysterious, the galactic halo. This isn't a halo in the traditional sense. It's not a ring or a crown. It's a roughly spherical region extending hundreds of thousands of light-years beyond the main disk, containing old stars, globular clusters, stellar streams, and something else. Something that doesn't interact with light at all. Globular clusters are ancient, spherical collections of stars, each cluster containing hundreds of thousands or even millions of stars packed into a region only a few dozen light-years across. The Milky Way has about 150 known globular clusters, though there are likely more hidden behind the galactic disk. These clusters are relics of the early galaxy, formed billions of years ago when the Milky Way was young. The stars within them are metal-poor. They contain very few elements heavier than hydrogen and helium, because they formed before generations of stars had lived and died, producing the heavier elements through nuclear fusion and supernova explosions. Omega Centauri, the largest globular cluster associated with the Milky Way, contains roughly 10 million stars and has a total mass of about 4 million solar masses. It's so large that some astronomers think it might not be a true globular cluster at all, but rather the remnant core of a dwarf galaxy that was absorbed by the Milky Way billions of years ago, its outer stars stripped away by tidal forces. The galactic halo also contains individual stars, scattered thinly through the vast space beyond the disk. These halo stars have unusual orbits. Many of them move in elongated ellipses that take them far from the galactic plane, or even orbit perpendicular to the disk. Their motions tell us they weren't born in the disk like most stars. They came from somewhere else. Many halo stars are the remnants of dwarf galaxies consumed by the Milky Way over billions of years. When these smaller galaxies were torn apart, their stars were scattered throughout the halo, retaining some memory of their original orbits. And pervading the entire halo, invisible and mysterious, is dark matter. The galactic halo is dominated by dark matter, an invisible substance that makes up roughly 85% of the galaxy's total mass. We can't see it, we can't detect it directly, we only know it exists because of its gravitational effects on the things we can see. Dark matter doesn't emit light, it doesn't absorb light, it doesn't reflect light, it doesn't interact with electromagnetic radiation in any way we've been able to detect. It's called dark not because it's black, but because it's invisible, completely transparent to all forms of light. The Milky Way you see in images, the beautiful spiral of stars and nebulae, is just the tip of the iceberg. Most of our galaxy is invisible. You are here. That's the most disorienting statement in all of astronomy, because here is a very specific, very strange place that's simultaneously ordinary and extraordinary. The solar system resides in a minor spiral arm called the Orion Arm, or sometimes the Orion Spur. Astronomers debate whether it qualifies as a full spiral arm or just a smaller branch connecting two major arms. We're located about 26,000 light-years from the galactic center, though this distance is uncertain by several thousand light-years. Some measurements suggest 25,000 light-years, others say 28,000. The dust and intervening material make precise measurements difficult.
We're roughly halfway out from the core to the edge of the visible disk. If the Milky Way were a city, we'd be living in the suburbs, not downtown and not in the rural outskirts, but somewhere in between.
Our position isn't particularly special. There's nothing unique about this part of the galaxy. We're not near the center where things get chaotic and dangerous. We're not at the edge where stars are sparse and lonely. We're in a relatively quiet region, far enough from the core to avoid intense radiation and gravitational disruptions, but close enough to be part of the galaxy's main structure.
The neighborhood around us is fairly typical for this part of the galaxy. Stars are separated by about 4 to 5 light-years on average, though the distances vary widely. Some regions have stars packed more closely together. Others have vast empty spaces where stars are rare.
The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system, about 4.24 light-years away. That's the closest star, and it's still so far away that light takes 4.24 years to travel from there to here. At the speed of our fastest spacecraft, it would take tens of thousands of years to reach Proxima Centauri. The next nearest stars are Barnard's star at 6 light-years, Wolf 359 at 7.9 light-years, Lalande 21185 at 8.3 light-years. Within 20 light-years of the Sun, there are only about 130 known star systems. Within 100 light-years, perhaps 14,000 stars. That's our immediate neighborhood, and it's sparsely populated compared to other regions of the galaxy.
Some scientists think this Goldilocks zone, not too close to the center, not too far toward the edge, might be necessary for complex life. Too close to the center, and stellar explosions become frequent. Supernovae, gamma-ray bursts, radiation from the supermassive black hole. All of these could strip away planetary atmospheres or sterilize worlds with intense radiation.
Too far out toward the galactic edge, and there aren't enough heavy elements, carbon, oxygen, nitrogen, iron, silicon, to form rocky planets and the complex chemistry necessary for life as we know it. These elements are created inside stars and scattered into space when stars die. In the outer reaches of the galaxy, stars are more pristine, containing mostly hydrogen and helium from the Big Bang, with fewer heavy elements. But whether our location is lucky or inevitable, we may never know. We've only discovered one example of complex life, ourselves, and we don't know whether we're typical or extraordinary.
Now, here's something that should make you feel a little dizzy. You're moving through space right now. Fast.
Earth orbits the Sun at about 30 kilometers per second. That's already difficult to comprehend. 108,000 kilometers per hour, fast enough to circle the Earth's equator in less than 25 minutes. You're moving at that speed right now, and you can't feel it because everything around you is moving at the same speed. But the Sun isn't stationary. It's orbiting the galactic center, dragging Earth and the other planets along with it. And we're moving fast, approximately 220 kilometers per second relative to the galactic center. That's nearly 800,000 kilometers per hour. Think about that for a moment. Every second, you travel 220 kilometers through the galaxy. Every hour, 800,000 kilometers. In the time it takes you to read this sentence, you've moved thousands of kilometers through space. At this speed, the solar system completes one orbit around the Milky Way roughly every 225 to 250 million years, a period sometimes called a galactic year or cosmic year. The uncertainty in this number reflects our uncertainty about the galaxy's mass and structure. Think about that. The last time Earth was in this exact position in the galaxy, dinosaurs hadn't evolved yet. Reptiles were just beginning to dominate the land, recovering from the Permian extinction, the worst mass extinction in Earth's history, which wiped out about 90% of all species. The supercontinent Pangaea was starting to form, bringing all of Earth's landmasses together into one giant continent. Since then, Earth has made one complete lap around the galaxy. Pangaea formed, existed for 100 million years, then broke apart. Dinosaurs evolved, dominated for 165 million years, then went extinct. Mammals rose to prominence. Primates evolved. Hominids split from other apes. Humans emerged, developed language, art, agriculture, civilization, technology. All of that, all of human history, all of recorded civilization, all of prehistory going back millions of years, is a tiny fraction of a single galactic orbit. Humans have existed for only about 300,000 years. That's roughly 0.1% of one galactic year. All of recorded history, the past 5,000 years, is 0.002% of one orbit. We're newcomers to this position in the galaxy. By the time we return to this spot, if humanity still exists, we'll be unrecognizable. And the motion doesn't stop there. The Milky Way itself is moving through space. The entire galaxy is falling toward the Andromeda galaxy at about 110 kilometers per second due to their mutual gravitational attraction. But simultaneously, the Milky Way is moving in other directions due to the gravitational pull of nearby galaxy clusters and large-scale cosmic structures. The local group, our small cluster of galaxies, including the Milky Way, Andromeda, Triangulum, and several dozen dwarf galaxies, is falling toward the Virgo supercluster, an enormous concentration of thousands of galaxies about 65 million light-years away. The local group is moving at about 600 kilometers per second relative to the cosmic microwave background, the afterglow of the Big Bang, which serves as a sort of universal reference frame. And the Virgo supercluster itself is being pulled toward an even larger structure called the Great Attractor, a gravitational anomaly located roughly 150 to 250 million light-years away, hidden behind the Milky Way's disk so we can't observe it directly.
Beyond that, the Great Attractor and surrounding structures are flowing toward the Shapley supercluster, one of the largest concentrations of galaxies in the observable universe.
You're not just moving. You're falling through space on multiple scales simultaneously, in multiple directions, at hundreds of kilometers per second, caught in gravitational currents shaped by structures spanning hundreds of millions of light years. And you can't feel any of it. You can't feel Earth's rotation. You can't feel Earth's orbit around the Sun. You can't feel the Sun's orbit around the galaxy. You can't feel the galaxy's motion through space. Everything around you is moving at the same speed, in the same direction, so there's no sensation of motion. You're in freefall, and freefall feels like floating. The night sky we see is a snapshot of our local neighborhood, a temporary arrangement of stars that happens to be near us right now. Over tens of thousands of years, the constellations will change. Stars that seem close together in the sky are actually at vastly different distances, moving in different directions at different speeds. Orion, one of the most recognizable constellations, won't look the same in 50,000 years. The stars that form the Hunter's belt, shoulders, and feet are moving in different directions. Some are approaching us, others are receding. The constellation is slowly stretching, distorting, coming apart. The Big Dipper, part of Ursa Major, is also temporary. In 100,000 years, it will be unrecognizable. The stars will have drifted, their positions changed by their individual motions through space. Even the stars themselves are temporary residents of the galaxy's spiral arms. The Sun, for example, passes through spiral arms periodically as it orbits the galactic center. Right now, we're near the inner edge of the Orion arm. In a few tens of millions of years, we'll drift out of this arm and into the space between arms. Some scientists have speculated that Earth's passage through spiral arms might correlate with mass extinctions, though the evidence is controversial. The idea is that spiral arms contain more dust and debris, increasing the chances of comet impacts on Earth, or that nearby supernovae in the dense spiral arms could bathe Earth in harmful radiation. But the correlation is weak, and the mechanisms are uncertain. We're still learning how the galaxy's structure affects planetary conditions over geological timescales. Nothing in the galaxy is fixed. Everything is in motion, following paths shaped by gravity across millions and billions of years. And we're just along for the ride, spinning through space, unable to step back and see the whole picture. trying to understand the cosmic currents carrying us forward.
Now we need to talk about the biggest mystery in the Milky Way.
Actually, it's bigger than that. It's the biggest mystery in all of modern astrophysics, cosmology, and physics itself. In the 1970s, astronomer Vera Rubin made an observation that shouldn't have been possible. She was studying how fast stars orbit in galaxies, measuring their velocities at different distances from the galactic center using spectroscopy, analyzing the light from stars to determine how quickly they're moving toward or away from us. According to Newton's laws of gravity and Einstein's refinements in general relativity, stars farther from the center should orbit more slowly, just like planets in our solar system. Mercury, closest to the Sun, orbits at about 47 kilometers per second. Venus orbits at 35 kilometers per second. Earth at 30 kilometers per second. Mars at 24 kilometers per second. Neptune, far from the Sun in the outer solar system, orbits at only 5.4 kilometers per second. This makes intuitive sense. Gravity weakens with distance, so objects farther out feel less gravitational pull and move more slowly. Rubin expected to find the same pattern in galaxies. Stars near the galactic center should orbit quickly, while stars in the outer regions should orbit more slowly, their speeds dropping off as they get farther from the center. But that's not what she found. Stars at the edge of galaxies were moving just as fast as stars closer to the center. In some cases, they were even moving faster than they should based on the visible mass of the galaxy. And this wasn't unique to one galaxy. It was happening everywhere she looked. Spiral galaxies, elliptical galaxies, dwarf galaxies. All of them showed the same strange behavior. The orbital velocities of stars weren't dropping off with distance. They were staying roughly constant, creating what astronomers call a flat rotation curve. This shouldn't be possible. If gravity is the only force holding galaxies together, and if the visible matter, stars, gas, dust, is all the mass that exists, then stars in the outer regions should be moving too slowly to match observations. Or, to put it another way, stars at the edges of galaxies are moving so fast that they should fly apart, escaping the galaxy's gravitational pull and dispersing into intergalactic space. But they don't. Something was holding galaxies together, something invisible. The only way to explain Rubin's observations was simple and terrifying. There's more mass in galaxies than we can see. A lot more. And it's distributed in a way that doesn't match the visible matter. This invisible mass came to be called dark matter. The term is slightly misleading. Dark matter isn't dark in the sense of being black or absorbing light. It's transparent. It's invisible. It doesn't interact with light in any way. Doesn't emit it, doesn't absorb it, doesn't reflect it, doesn't scatter it. Light passes through dark matter as if it isn't there. But gravitationally, dark matter is very much present, and it's everywhere. In the Milky Way, dark matter forms an enormous halo, extending hundreds of thousands of light years beyond the visible disk. This halo isn't a perfect sphere. It's slightly flattened, shaped by the galaxy's rotation and interactions with nearby galaxies. And it contains approximately 10 times more mass than all the stars, gas, and dust in the galaxy combined. Let that sink in for a moment. Everything you can see in the night sky, every star, every nebula, every glowing gas cloud, every planet orbiting every star, represents less than 10% of the Milky Way's total mass. The other 90% is dark matter, invisible and undetectable except through gravity. Without dark matter, the Milky Way shouldn't exist. The stars in the outer regions of the galaxy are moving so fast, remember, we're moving at 220 kilometers per second, that they should have escaped long ago, flying off into intergalactic space and leaving behind a small, dense cluster of stars near the galactic center. But the dark matter halo provides the extra gravity needed to hold everything together. It's like an invisible net, keeping stars bound to the galaxy even as they hurtle through space at hundreds of kilometers per second. The galaxy isn't held together by stars. It's held together by an invisible scaffolding we can't see and barely understand. Computer simulations of galaxy formation consistently show that without dark matter, galaxies like the Milky Way can't form.
The visible matter alone doesn't have enough gravity to pull itself together into stable structures. Without dark matter, the universe would be very different, perhaps filled with diffuse gas clouds and small, unstable clusters of stars, but no grand spiral galaxies like the one we inhabit. Dark matter isn't just important to the Milky Way, it's crucial to the structure of the entire universe. Galaxy clusters, groups of hundreds or thousands of galaxies bound together by gravity, wouldn't exist without dark matter. The cosmic web, the large-scale structure of the universe, with galaxies arranged in filaments and sheets surrounding vast voids, is shaped primarily by dark matter. Dark matter was there in the early universe, its gravity pulling normal matter together into the first stars and galaxies. It's been shaping the universe for 13.8 billion years, invisible but essential.
What is dark matter? Honestly, we don't know. And that's not a cop-out or an exaggeration. Despite decades of research, hundreds of experiments, and thousands of scientific papers, we still don't know what dark matter is made of. It could be exotic particles that interact with normal matter only through gravity. Theoretical particles with names like WIMPs, or weakly interacting massive particles. These hypothetical particles would be created in the Big Bang, would have mass, but would interact with normal matter so weakly that they pass through everything, through Earth, through you, through detectors, without leaving a trace. Scientists have built incredibly sensitive detectors deep underground to try to catch dark matter particles. These detectors are placed in mines or tunnels, sometimes more than a kilometer below the surface, to shield them from cosmic rays and other sources of background radiation that might produce false signals. The detectors contain materials like liquid xenon or germanium crystals, chilled to extremely low temperatures. The idea is that if a dark matter particle collides with an atomic nucleus in the detector, it will produce a tiny flash of light or a small amount of heat, a signal that can be measured and analyzed. So far, nothing. Decades of searching, increasingly sensitive experiments, larger and larger detectors. No confirmed dark matter particles. It could be axions, another hypothetical particle predicted by theories trying to solve problems in particle physics. Axions would be extremely light, billions of times lighter than electrons, and would interact with matter even more weakly than WIMPs. They're incredibly difficult to detect, requiring specialized experiments using powerful magnetic fields to convert axions into detectable photons. It could be sterile neutrinos, a hypothetical type of neutrino that doesn't interact through the weak nuclear force like ordinary neutrinos. Sterile neutrinos would be essentially invisible, detectable only through their gravitational effects and possibly through their decay into ordinary neutrinos. It could be primordial black holes formed in the first moments after the Big Bang, not from the collapse of stars. These black holes could range in size from microscopic to thousands of solar masses, and they would be invisible unless they're actively consuming matter or passing in front of a background star, causing gravitational lensing. Or it could be something stranger, something that doesn't fit into our current understanding of physics at all. Some physicists have proposed modified theories of gravity, alternatives to Einstein's general relativity that would produce the same effects we attribute to dark matter without requiring any invisible matter. These theories, collectively called MOND, modified Newtonian dynamics, and its relativistic extensions, suggest that gravity behaves differently on very large scales, producing stronger gravitational effects than we'd expect from visible matter alone. But MOND theories have problems. They can explain the rotation curves of galaxies reasonably well, but they struggle to explain other observations, like gravitational lensing, the bending of light by gravity, or the precise patterns in the cosmic microwave background radiation. Most physicists still favor the dark matter explanation, but the door isn't completely closed on alternative theories. The truth is, we're still searching. Every major physics experiment, every new telescope, every theoretical framework in cosmology is, in some way, trying to solve the dark matter problem. The Large Hadron Collider at CERN searches for dark matter by trying to create it in high-energy particle collisions. Underground detectors wait patiently for dark matter particles to pass through and interact. Space telescopes look for gamma rays that might be produced when dark matter particles collide and annihilate each other. Radio telescopes search for signals from axions interacting with magnetic fields. And we keep coming up empty. This is one of the most humbling aspects of modern science. We've sent spacecraft to the edge of the solar system. We photographed black holes. We've detected gravitational waves from colliding neutron stars billions of light years away. We've decoded the human genome and developed quantum computers. But we don't know what 85% of the matter in the universe is made of. And until we do, we have to accept an uncomfortable truth. Most of the Milky Way is invisible to us. We live inside a structure we can't fully see or understand, held together by forces we can't explain, shaped by a substance we can't detect. The galaxy is far stranger than it appears, and the visible part, the stars and nebulae, the glowing gas clouds and star-forming regions, is just the surface, the visible expression of a much larger invisible structure. We're like insects crawling on the surface of an enormous sculpture, able to see and touch only the outermost layer, unable to perceive the framework that holds it all together. The Milky Way looks calm, majestic, eternal, like a cosmic work of art, frozen in time, unchanging over billions of years. It's none of those things. Our galaxy is a cannibal. It has spent billions of years devouring smaller galaxies, tearing them apart and absorbing their stars. And the evidence is written across the sky, in the positions and velocities of stars, in the chemical compositions of stellar populations, in the streams and shells of debris that litter the galactic halo. And this isn't ancient history. It's happening right now. When astronomers map the positions and velocities of stars in the galactic halo, they find something strange. Streams of stars moving together in coherent flows, like rivers in space. These stellar streams are the remnants of dwarf galaxies that wandered too close to the Milky Way and were torn apart by tidal forces. Imagine a small galaxy containing millions or tens of millions of stars approaching the Milky Way. At first, nothing happens. The dwarf galaxy orbits peacefully, held together by its own gravity. But as it gets closer to the Milky Way, our galaxy's gravity begins to pull harder on the near side of the dwarf galaxy than on the far side. This difference in gravitational force, called a tidal force, the same force that creates ocean tides on Earth, stretches the smaller galaxy. The stars on the near side are pulled toward the Milky Way more strongly than the stars on the far side. Over time, this stretching elongates the dwarf galaxy, pulling it apart like taffy. Eventually, after several orbits around the Milky Way, the dwarf galaxy disintegrates completely. Its stars don't disappear, they join the Milky Way's halo, but they retain some memory of their original motion. They continue moving together in streams, forming long arcs that can persist for billions of years, slowly dispersing and mixing with the Milky Way's native population. One of the most famous examples is the Sagittarius dwarf elliptical galaxy, usually called Sagittarius Stream or SGR-DSPH. This small elliptical galaxy, discovered in 1994, is located about 70,000 light-years from Earth, on the far side of the galactic center. It contains roughly 4 billion stars, or at least it used to. Sagittarius Stream has been orbiting the Milky Way for billions of years, and each time it passes close to our galaxy, swinging through the galactic disk, more of its stars are stripped away by tidal forces. Today, the Sagittarius Stream wraps around the Milky Way multiple times, a ghostly trail marking the slow death of an ancient galaxy. The stream extends across more than 360 degrees of the sky, a complete loop around the celestial sphere. Parts of it pass above the galactic plane, parts below. It's one of the most prominent features in the galactic halo. Though it's invisible to the naked eye, the individual stars are too faint and scattered. In another few billion years, Sagittarius Stream will be completely absorbed. Its stars will be scattered throughout the Milky Way's halo, mixed with stars from other consumed galaxies and the Milky Way's native population, indistinguishable from each other except through careful analysis of their orbits and chemical compositions. And Sagittarius Stream isn't alone. Astronomers have identified dozens of stellar streams in the galactic halo, each one the fossil of a galaxy that no longer exists. The Monoceros ring, the stream of stars encircling the Milky Way's disk. The Virgo stellar stream, stretching across the sky. The Orphan stream, so named because astronomers haven't yet identified its parent galaxy. The source galaxy has been completely destroyed, but its trail of stars remains. Some of these streams are young, only a few 100 million years old, still visible as coherent structures with stars clustered together. Others are ancient, billions of years old, their stars scattered and dispersed by the Milky Way's gravity. These old streams are harder to detect. They require careful analysis of stellar velocities and chemical compositions to identify stars that originated in the same parent galaxy. Each stream tells a story of galactic cannibalism, a dwarf galaxy that came too close and paid the ultimate price. But small dwarf galaxies aren't the only victims. The Milky Way has consumed larger galaxies too, and those collisions have shaped our galaxy's structure in fundamental ways. Several billion years ago, estimates range from 8 to 11 billion years ago, the Milky Way collided with a dwarf galaxy that astronomers have named Gaia Enceladus, after the European Gaia spacecraft that helped discover it, and the giant Enceladus from Greek mythology. Gaia Enceladus was substantial. It contained at least several billion stars, possibly tens of billions, making it one of the largest galaxies the Milky Way has ever absorbed. It was roughly 1/4 the mass of the Milky Way at the time, not a small snack, but a significant meal. When Gaia Enceladus collided with the Milky Way, the impact was catastrophic for both galaxies. The collision didn't destroy the Milky Way, but it disrupted our galaxy's structure, possibly puffing up the galactic disk, triggering intense bursts of star formation, and reshaping the distribution of stars in the halo. We know this happened because astronomers using data from the Gaia spacecraft have identified populations of stars with unusual properties. These stars have retrograde orbits. They orbit in the opposite direction from most stars in the galactic disk. They have high velocities relative to the galactic center, and their chemical compositions are different from stars born in the Milky Way. Chemical composition is crucial for understanding a star's origin. Stars born in different galaxies have different chemical signatures because they formed from gas clouds with different histories. The ratio of elements like iron to hydrogen or magnesium to iron varies depending on how many generations of stars lived and died before the current generation formed. Stars from Gaia Enceladus have characteristic chemical patterns that mark them as foreigners, born elsewhere, now living in the Milky Way. In fact, some of the stars you see in the night sky aren't native to the Milky Way. They're immigrants, refugees from a galaxy that no longer exists. They've been absorbed into our galaxy, but they carry chemical memories of their birthplace. The globular cluster Omega Centauri, mentioned earlier, is probably the remnant core of a dwarf galaxy consumed by the Milky Way. Most globular clusters contain stars with very similar chemical compositions. They all formed from the same gas cloud at roughly the same time. But Omega Centauri contains stars with a wide range of compositions, suggesting multiple generations of star formation, which is more consistent with a dwarf galaxy than a simple globular cluster. Omega Centauri might be the last surviving piece of a much larger galaxy, its outer stars stripped away by the Milky Way's gravity, leaving only the dense core behind. And the process continues. The Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere, the Large Magellanic Cloud and Small Magellanic Cloud, are currently being consumed by the Milky Way. The Large Magellanic Cloud, or LMC, is about 160,000 light-years away and contains roughly 30 billion stars. It's the fourth largest galaxy in the local group, after Andromeda, the Milky Way, and Triangulum. The Small Magellanic Cloud, or SMC, is about 200,000 light-years away and contains roughly 3 billion stars. Both are losing mass. They're surrounded by streams of gas, primarily hydrogen, being pulled away by the Milky Way's tidal forces. These streams, called the Magellanic Stream and Leading Arm, extend across enormous distances, trailing behind and ahead of the clouds as they orbit the Milky Way. The Magellanic Stream alone stretches across more than 200 degrees of the sky and contains enough gas to form hundreds of millions of new stars. This gas was once part of the Magellanic Clouds, but it's being stripped away and will eventually fall into the Milky Way's disk, fueling new star formation. The clouds themselves are doomed. In a few billion years, estimates vary, but most models suggest 2 to 4 billion years, they will spiral inward and merge with the Milky Way. The Large Magellanic Cloud might survive for a while as a distinct structure, but eventually it too will be torn apart, its stars absorbed into the Milky Way's halo and disk. This is how galaxies grow, not peacefully, not gradually, but through violence and consumption. The Milky Way has absorbed dozens, perhaps hundreds of smaller galaxies over its lifetime. Every one of those galaxies had its own history, its own stellar populations, its own unique characteristics.
Now they're part of us. Their stars orbit the Milky Way. Their gas contributes to new star formation. Their histories are encoded in the chemical compositions and orbital patterns of stars scattered throughout the halo.
The Milky Way is a mosaic, built from the fragments of countless smaller galaxies over billions of years. We're not a pure, pristine galaxy. We're a composite, assembled piece by piece through mergers and collisions.
And soon we'll face our biggest challenge yet.
The Andromeda Galaxy is 2.5 million light-years away. That sounds far, and it is far. Light takes 2.5 million years to travel from Andromeda to us. When you look at Andromeda in the night sky, it's visible as a faint smudge to the naked eye from dark locations. You're seeing it as it was 2.5 million years ago, when our ancestors were early hominins in Africa, just beginning to use stone tools. But 2.5 million light-years isn't that far on cosmic scales, and Andromeda isn't stationary. It's moving toward us at approximately 110 kilometers per second. That might not sound impressive compared to the speeds we've been discussing. The Sun orbits the galactic center at 220 kilometers per second. But over cosmic timescales, it's more than enough. In roughly 4.5 billion years, the Milky Way and Andromeda will collide. The two largest galaxies in the local group, each containing hundreds of billions of stars, each spanning hundreds of thousands of light-years, are on a collision course, and there's nothing that can stop it. Gravity is patient. Gravity is inexorable. Two massive galaxies, separated by only 2.5 million light-years, will inevitably fall together. But collision might be the wrong word. It evokes images of violence, destruction, stars smashing into each other like cars in a highway pileup. That's not what will happen. When galaxies collide, stars almost never hit each other. This is one of the most counterintuitive facts in astronomy. You'd think that when two galaxies, each containing hundreds of billions of stars, merge, there would be countless stellar collisions. But space is so vast, and stars are so small relative to the distances between them, that the chance of two stars colliding is incredibly small. To put this in perspective, if the Sun were the size of a grain of sand, the nearest star would be about 30 kilometers away. Stars are tiny compared to the distances separating them. Even in a galactic merger, when two galaxies pass through each other, most stars sail past each other without ever getting close. What does happen is far stranger and more beautiful. As the two galaxies approach each other, their gravitational fields begin to interact. The spiral arms of both galaxies will be disrupted, stretched and torn by tidal forces. Long streamers of stars will be flung into intergalactic space, arcing away from the collision site in graceful curves hundreds of thousands of light-years long. Computer simulations of the Milky Way-Andromeda collision show these tidal tails forming, massive plumes of stars ejected from both galaxies. Some of these stars will escape entirely, becoming intergalactic wanderers, orphaned from their parent galaxies. Others will eventually fall back, pulled by gravity to rejoin the merged galaxy millions of years later. The spiral structure of both galaxies will be destroyed. The beautiful pinwheel shapes, the graceful curves of the spiral arms, all of it will be disrupted by the collision. By the time the merger is complete, the resulting galaxy will no longer be a spiral. It will be an elliptical galaxy, a roughly spherical or elongated ball of stars with no disk, no spiral arms, no distinct structure. But the most traumatic effect will be on the gas. Both the Milky Way and Andromeda contain vast reservoirs of cold hydrogen gas, raw material for star formation. When the two galaxies collide, their gas clouds will smash together. And when gas clouds collide at high speeds, they don't pass through each other like stars do. They compress, heat up, and form new stars. The collision will trigger one of the most intense periods of star formation in the history of both galaxies. Millions, perhaps billions, of new stars will be born as gas clouds collide and collapse. Massive stars, bright, hot, and short-lived, will form in enormous numbers, illuminating vast nebulae with their radiation. For a brief period, brief in cosmic terms, lasting millions of years, the merged galaxy will blaze with light. Supernovae will explode throughout the galaxy as massive stars exhaust their fuel and collapse. Star-forming regions will dot the galaxy, glowing regions of hot gas where new solar systems are being born. From a distance, the collision would be spectacular, a cosmic fireworks show playing out over millions of years. For a brief time, the merged galaxy might be one of the brightest objects in the local group, outshining all its neighbors. But this is just the beginning. The two galaxies won't merge immediately. They'll pass through each other, their mutual gravitational interaction slowing them down, dissipating their orbital energy. Then they'll fall back together and collide again, and possibly a third time. Each collision will release energy, converting the kinetic energy of the galaxy's motion into heat, radiation, and the violent shuffling of stars and gas. Each passage will bring the cores of the two galaxies closer together. Eventually, after several collisions over 1 billion years or more, the Milky Way and Andromeda will merge completely, forming a single, enormous elliptical galaxy that astronomers have already given a name, Milkomeda, sometimes called Milkdromeda. The supermassive black holes at the centers of both galaxies, Sagittarius A in the Milky Way and the larger black hole at Andromeda's core, will spiral together and eventually merge, creating an even more massive black hole containing tens of millions of solar masses. The merger of two supermassive black holes is one of the most energetic events in the universe, releasing enormous amounts of energy in the form of gravitational waves, ripples in space-time itself. If any civilizations exist in Milkomeda at that time, and if they have gravitational wave detectors, they'll record one of the strongest signals ever observed. And Earth? If Earth still exists, and that's a big if, it will be part of Milkomeda. Here's the problem. The merger with Andromeda will occur roughly 4.5 billion years from now, but the Sun is already 4.6 billion years old, about halfway through its main sequence lifetime. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin burning hydrogen in a shell around the core. This will cause the Sun to expand, becoming a red giant. As a red giant, the Sun will grow to perhaps 100 or 200 times its current radius, possibly reaching Earth's orbit. The exact details are uncertain. Stellar evolution models have significant uncertainties when predicting the red giant phase, but it's possible that Earth will be engulfed by the Sun's outer atmosphere and vaporized. Even if Earth survives, it won't be habitable. The Sun's increased luminosity will heat Earth's surface to temperatures where the oceans boil away, the atmosphere is stripped into space, and the surface becomes a scorched, lifeless rock. So by the time the Milky Way and Andromeda collide, Earth, if it hasn't been destroyed, will already be long dead, a burned-out cinder orbiting a dying star. But let's assume, for the sake of argument, that humanity or its descendants have survived, perhaps by colonizing other star systems, or by building artificial habitats, or by uploading consciousness into machines, or through means we can't currently imagine. If humans are still around to witness the collision, what will they see? Surprisingly little on a day-to-day basis. Galactic collisions happen slowly. Even at their peak, the changes occur over millions of years, far too gradually for any individual observer to perceive. You wouldn't look up and see stars visibly moving or the sky changing before your eyes. Instead, over thousands of generations, astronomers would observe subtle changes. The shape of the Milky Way would gradually distort. New stars would appear, born in collapsing gas clouds triggered by the collision. The night sky would slowly grow brighter as the density of stars increased. Andromeda, currently a faint smudge in the sky, would grow larger and brighter over millions of years, gradually resolving into individual stars, its spiral structure becoming visible, its core glowing brighter as it approached. Eventually, millions of years after the first close pass, Andromeda would dominate the sky, a massive spiral galaxy filling the view, its spiral arms stretching across the celestial sphere. And then it would pass through, the two galaxies interpenetrating, stars from both galaxies mingling together. The Sun's position in the new galaxy would likely change. Computer simulations suggest our solar system has about a 12% chance of being ejected from the merged galaxy entirely, flung into intergalactic space by gravitational interactions during the collision. There's a small chance, maybe 3%, that the Sun could be captured by Andromeda's gravity and pulled toward the merged galaxy's core, ending up much closer to the central black hole than we are now. Most likely, though, about 85% probability, the Sun will remain part of the merged galaxy, flung into a new orbit, possibly ending up farther from the galactic center than we are now, or possibly closer. The night sky will be unrecognizable, filled with stars from both the Milky Way and Andromeda, their populations thoroughly mixed. But here's the most important part. If humans, or whatever we've evolved into by then, are still around, still inhabiting planets or habitats orbiting stars, their daily lives will continue mostly unchanged. Stars will continue to shine. Planets will continue to orbit their suns. Life, if it still exists, will continue. The collision will be catastrophic on a galactic scale, reshaping the structure of two enormous galaxies, but graceful on a human scale. No apocalyptic explosions, no sudden catastrophes, just slow, gradual change over millions of years. And after it's over, after the last merger, after the chaos subsides and the new galaxy settles into a stable configuration, Milky Way will be a different kind of galaxy. Larger, more massive, an elliptical galaxy instead of a spiral, containing 1 trillion stars instead of a few hundred billion. But it will still be a galaxy. Stars will still shine, planets will still orbit. And perhaps, somewhere in that distant future galaxy, something will look up at the night sky, now filled with stars from two ancient galaxies, and wonder about its place in the cosmos. Just as we do now. For decades, astronomers have been trying to see through the dust. They've built radio telescopes to observe the galaxy and wavelengths that penetrate dust clouds. They've launched infrared telescopes into space to escape Earth's atmosphere, which blocks much of the infrared light from reaching the ground. But nothing has matched the power of the James Webb Space Telescope. JWST, launched on December 25, 2021, and deployed over 1 million miles from Earth at the second Lagrange point, is revolutionizing our understanding of the Milky Way, and it's doing it by looking at the galaxy in a way we've never been able to before. JWST observes the universe in infrared wavelengths, light with longer wavelengths than visible light, wavelengths that human eyes can't see, but which carry crucial information about cool objects and obscured regions. And infrared light has a superpower. It can pass through cosmic dust almost unhindered. Remember the problem we discussed earlier? The galactic center is hidden by vast clouds of dust that block visible light. To optical telescopes like Hubble, the core of the Milky Way is shrouded, obscured by trillions of tiny particles floating in interstellar space. But to JWST, it's clear. Infrared light has wavelengths longer than the size of dust particles, so instead of being absorbed or scattered, it passes around them, diffracting through the dust clouds and continuing on its way. It's like the difference between shouting through a chain-link fence, the sound waves pass through easily, versus throwing baseballs through it. They get blocked. In its first year of operations, JWST captured stunning images of the galactic center, revealing structures that had never been seen before. Massive star-forming regions glowing with infrared light. Clusters of young, massive stars heating the surrounding gas. Intricate filaments of dust and gas sculpted by stellar winds and radiation pressure. Dense knots where new stars are being born, hidden inside cocoons of dust. One of the most remarkable discoveries was the sheer number of young stars near the galactic center. For years, astronomers thought star formation near Sagittarius A should be suppressed. The intense radiation from the supermassive black hole and nearby stars should heat the gas, preventing it from cooling and collapsing to form new stars. The tidal forces from the black hole's gravity should rip apart gas clouds before they can collapse. But JWST revealed that's not the case. Stars are forming in the galactic center, even in the harshest environment in the galaxy. Massive stars, tens of times the mass of the Sun, are being born within just a few light-years of Sagittarius A.
How is this possible? We don't fully understand yet. Some theories suggest that gas clouds need to be extremely dense to overcome the hostile conditions, so dense that their self-gravity overwhelms the tidal forces and radiation pressure. Others propose that collisions between gas clouds compress them enough to trigger collapse. The exact mechanisms are still being worked out.
JWST has also been mapping the spiral arms of the Milky Way in unprecedented detail. By observing young, massive stars, which shine brightly in infrared, and the nebulae surrounding them, astronomers are slowly piecing together the galaxy's structure, building a more accurate map than ever before.
And what they're finding is that the Milky Way is more complicated than anyone expected.
The spiral arms aren't smooth, continuous structures. They're fragmented, with gaps and branches and unexpected features. Some regions of the arms are actively forming stars, glowing with the light of hot young stars and the infrared glow of warm dust. Other regions seem dormant, containing older stars but little ongoing star formation. The bar at the center of the galaxy is more prominent than previous observations suggested. New measurements indicate it might be longer and more massive than we thought, extending farther out from the core and influencing the motion of stars throughout the inner galaxy.
And the galaxy's structure varies depending on which tracer you use to map it. If you map young, massive stars, you get one picture of the spiral arms. If you map older stars, you get a slightly different picture. If you map dense molecular clouds, regions of cold gas where stars form, you get yet another picture.
This suggests that the spiral arms aren't simple density waves affecting all components of the galaxy equally. Different types of objects respond differently to the density waves, creating multiple overlapping patterns.
Every new observation reveals more complexity, more questions, more mysteries.
But JWST isn't working alone. It's part of a fleet of instruments, each contributing unique information to our understanding of the galaxy. The Gaia spacecraft, operated by the European Space Agency, has been mapping the positions, distances, and motions of over 1.8 billion stars in the Milky Way, the most detailed 3D map of any galaxy ever created. Gaia measures stellar positions with incredible precision, accurate to within a few dozen microarc seconds, equivalent to measuring the width of a human hair from 1,000 kilometers away. But Gaia does more than just measure positions. It measures parallaxes, the apparent shift in a star's position as Earth orbits the Sun, which allows astronomers to calculate distances. And it measures proper motions, the slow movement of stars across the sky, which reveals how stars are moving through space. By combining these measurements, astronomers can reconstruct the three-dimensional motion of stars throughout the galaxy. They can identify stellar streams, remnants of destroyed dwarf galaxies. They can map the distribution of dark matter by studying how stars move through the galactic halo. They can trace the galaxy's past collisions and predict its future evolution. Gaia has revealed that the Milky Way's disk isn't flat. It warps and wobbles, like a vinyl record that's been slightly bent. The disk flares upward on one side and downward on the other, possibly due to gravitational interactions with the Magellanic Clouds, whose gravity is pulling on the outer regions of the galactic disk. Gaia has also discovered unexpected velocity patterns in stellar populations, groups of stars moving together in coherent streams, stars with unusual orbits that don't match models of the galaxy's formation, regions where the stellar density is higher or lower than expected. Each anomaly is a clue, a piece of evidence pointing towards some event in the galaxy's past. A merger, a collision, a gravitational disturbance that left its mark on stellar motions billions of years ago. Radio telescopes are mapping the distribution of hydrogen gas throughout the galaxy. The Very Large Array in New Mexico, the Arecibo Observatory, before its collapse in 2020, the Parkes Telescope in Australia, and others have created detailed maps showing where cold hydrogen gas is concentrated, the raw material for future star formation. These maps reveal enormous structures, molecular clouds spanning hundreds of light years, dense regions where stars will form in the next few million years, and vast empty regions where gas has been cleared away by stellar winds and supernova explosions. The galactic center appears particularly complex in radio observations. There are filamentary structures, long, thin threads of radio emission, possibly generated by magnetic fields interacting with charged particles. There are bubbles of hot gas, blown outward by stellar winds and supernovae. And there are regions of intense radio emission near Sagittarius A, possibly produced by particles accelerating to near light speeds in the black hole's magnetic field. X-ray telescopes like Chandra and XMM Newton observe the hottest, most energetic processes in the galaxy. They've captured images of supernova remnants, expanding shells of debris from exploded stars, glowing with X-rays as the shock waves heat the surrounding gas to millions of degrees. They've observed binary star systems where one star is pulling material off its companion, that material spiraling inward and heating up until it emits X-rays. And they've watched Sagittarius A flare, brief bursts of X-ray emission that occur when the black hole swallows a gas cloud or asteroid that wandered too close. These flares are unpredictable. Sagittarius A star is usually quiet, emitting relatively little radiation for such a massive black hole. But occasionally, something falls in, perhaps a comet or asteroid, perhaps a cloud of gas, and the black hole briefly flares to hundreds or thousands of times its normal brightness. These flares last anywhere from minutes to hours, then fade as the material is consumed. Ground-based optical telescopes continue to contribute as well, despite the limitations of observing through Earth's atmosphere. Large surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time are cataloging hundreds of millions of stars, building enormous databases of stellar positions, brightnesses, colors, and spectra. These surveys aren't just collecting data for its own sake. They're searching for patterns, correlations, anomalies. They're identifying rare types of stars, hypervelocity stars moving so fast they'll escape the galaxy, white dwarf binaries that will eventually merge and explode as supernovae, massive stars in the final stages of their lives about to explode. And all of this data is being combined, integrated, analyzed by supercomputers and machine learning algorithms. Artificial intelligence systems are learning to identify stellar streams in Gaia data, to classify stars by their spectra, to predict which stars are likely to explode as supernovae in the near future. We're slowly building a more complete picture of the Milky Way, combining observations across the entire electromagnetic spectrum, from radio waves to gamma rays, from the longest wavelengths to the shortest. But here's the thing, every answer raises new questions. Why does star formation continue near the galactic center despite the hostile environment? We have theories, but no definitive answer. Why is the bar so prominent, and why does it have the orientation it does? We can model bar formation, but we don't know why the Milky Way developed this particular bar. Why do some spiral arms have gaps? What creates the fragmented, branching structure we observe? Density wave theory explains smooth spiral arms reasonably well, but the real Milky Way is messier than the theory predicts. Why is the disk warped? Is it being pulled by the Magellanic Clouds, or is there some other cause? Perhaps an ancient collision with a dwarf galaxy, or the gravitational influence of dark matter substructure. What caused the strange velocity patterns Gaia has detected in certain stellar populations? Some stars are moving in ways that don't match any simple model of galactic dynamics. They're outliers, anomalies, mysteries. We're seeing the galaxy more clearly than ever before, but we're also realizing how much we still don't understand. Each new telescope, each new survey, each new dataset reveals phenomena that don't fit neatly into our theories. JWST can pierce through dust, revealing hidden star-forming regions and the galactic core in unprecedented detail. But it can't tell us how the galaxy formed or why it evolved the way it did. It shows us what exists now, but not why it exists. Gaia can map 1 billion stars, measuring their positions and motions with incredible precision. But there are hundreds of billions more stars that remain unmeasured, too faint, too distant, or hidden by dust. And Gaia can't measure dark matter at all, It can only infer its presence from the motions of visible stars. Radio telescopes can detect hydrogen gas, mapping the distribution of future star-forming material. But they struggle to see molecular hydrogen, H2, the most common form of hydrogen in dense clouds, because H2 doesn't emit radio waves efficiently. We have to infer its presence from other molecules like carbon monoxide. We're getting better at observing the Milky Way. Our instruments are more powerful, our techniques more sophisticated, our datasets larger and more comprehensive. But we're still a long way from truly understanding our home galaxy. And perhaps that's as it should be. Perhaps some mysteries are meant to remain unsolved. Not forever, but for now, keeping us curious, keeping us searching, keeping us humble in the face of cosmic complexity. So here's what we still don't know about our own galaxy, the cosmic structure we've lived inside for our entire existence as a species.
We don't know exactly how many stars the Milky Way contains. Estimates range from 100 billion to 600 billion, a factor of 6 uncertainty in one of the most basic properties of the galaxy. Every new survey refines that number. Gaia's data suggests something in the range of 200 to 400 billion, but we'll probably never have a precise count. Too many stars are too faint to detect. Too many are hidden behind dust. Too many are in regions we can't observe from Earth's position in the galaxy. We don't know the exact mass of the Milky Way. Estimates range from 1 trillion to 2 trillion solar masses, depending on the method used and the assumptions made about dark matter distribution. Different measurements give different results, and the uncertainties are substantial. This matters because the galaxy's mass determines its fate, how it will interact with Andromeda, how it responds to gravitational perturbations, how it will evolve over billions of years. We don't know the precise shape of the galaxy. We know it's a barred spiral, but the details remain fuzzy. How many major spiral arms does it have? 2? 4? Different studies give different answers. The Perseus arm and the Scutum Centaurus arm seem to be major structures, but are they the only major arms, or are there others? And what about the smaller spurs and branches? Are they transient features or permanent structures? The exact structure of the bar is also uncertain. How long is it? How massive? What angle does it make with our line of sight? Different observations using different tracers, old stars, young stars, gas, give slightly different answers, suggesting the bar might not be a simple uniform structure. We don't know why the Milky Way formed the way it did. Why a barred spiral? Why not an elliptical galaxy, like many galaxies in the universe? Why not an irregular galaxy without clear structure? Was it determined by the initial conditions of the gas cloud that collapsed to form the galaxy billions of years ago? Or was it shaped by the mergers and collisions it experienced over its lifetime? Galaxy formation is still not fully understood. We have good models of how dark matter halos form and how gas falls into those halos. We understand many of the processes involved: gas cooling, star formation, stellar feedback, supernova explosions. But the details remain uncertain, especially for galaxies as complex as the Milky Way. We don't fully understand how spiral arms persist. They're density waves, we know that much, but what maintains them? Why do they remain stable over hundreds of millions of years instead of winding up and disappearing? Some theories invoke self-gravity. The spiral arms maintain themselves through their own gravitational pull. Others suggest interactions with satellite galaxies help maintain the structure. Still others propose that bars drive the spiral pattern, funneling gas in ways that naturally create spiral waves. The truth is, we don't have a complete, definitive answer. We don't know what lies beyond the visible edge of the galaxy. The galactic disk extends about 100,000 light-years across, but the dark matter halo extends much farther, perhaps 500,000 light-years, perhaps more. How far? We're not sure. At what distance does the Milky Way's dark matter halo transition into intergalactic space? Is there a clear boundary? Or does the density gradually fade until it becomes indistinguishable from the cosmic background? We don't even know where the edge of the visible galaxy is precisely. The stellar density doesn't drop to zero abruptly. It fades gradually as you move outward. At some distance, the density becomes so low that distinguishing Milky Way stars from intergalactic stars becomes impossible. Where do you draw the line? We don't know whether the Milky Way is typical or unusual.
We can observe thousands of other galaxies across the universe, and most of them look broadly similar. Spiral structure, central bulge, stellar populations distributed in disks and halos. But is our galaxy average, or does it have unique features that make it special?
Some evidence suggests the Milky Way might be slightly unusual. It's one of the larger galaxies in the local group, but not the largest. Andromeda is bigger. Its star formation rate seems to be lower than expected for a galaxy of its mass, suggesting something is suppressing star formation. Its bar is prominent, but not all spiral galaxies have bars.
Compared to the wider universe, how does the Milky Way stack up? Is it typical of spiral galaxies in general, or is it an outlier in some way? Without better statistics, without observing many galaxies in as much detail as we observe the Milky Way, we can't say for certain.
We don't know how many planets in the Milky Way could harbor life. We can estimate the number of potentially habitable planets, worlds in the right temperature range, orbiting stable stars, with the right size and composition to maintain atmospheres and liquid water. Some estimates suggest billions of potentially habitable planets in the galaxy. Others are more conservative, putting the number in the millions.
But that doesn't tell us whether life actually exists on those worlds, or whether it's common or rare, or whether it ever evolves beyond simple microbes.
The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of intelligent civilizations in the galaxy by multiplying together various factors: the rate of star formation, the fraction of stars with planets, the fraction of planets that are habitable, the fraction where life actually arises, the fraction where life becomes intelligent, the fraction that develops technology, and how long such civilizations last. But most of these factors are deeply uncertain. We have no idea how likely it is for life to arise on a habitable planet. We don't know how likely it is for life to become intelligent. We don't know how long technological civilizations typically survive before destroying themselves or evolving into something unrecognizable.
The Fermi paradox highlights this uncertainty. If intelligent life is common in the galaxy, where is everyone? Why haven't we detected any signals? Why hasn't anyone visited Earth? The paradox has many proposed solutions. Maybe life is rare, maybe intelligence is rare, maybe technological civilizations destroy themselves quickly, maybe they're deliberately hiding, maybe they're using communication methods we haven't imagined, maybe the galaxy is too vast and travel between stars too difficult.
We don't know. We have one data point, ourselves, and one example isn't enough to draw conclusions.
We don't know what dark matter is. This is the biggest unsolved problem in astrophysics, and it's central to understanding the Milky Way. Dark matter makes up 85% or more of the galaxy's mass. It holds the galaxy together. It shaped the galaxy's formation. And we have no idea what it's made of. Until we solve this problem, until we detect dark matter particles directly, or find some alternative explanation for the phenomena we attribute to dark matter, we're missing the most important piece of the puzzle. We're trying to understand a structure where 85% of the mass is invisible and unknown. It's like trying to understand a building when you can only see 15% of it, and the rest is hidden behind a veil.
And there's something even more fundamental we don't know, something so basic it's easy to overlook.
We've never seen the Milky Way from the outside. Every image you've ever seen of the Milky Way as a spiral galaxy, every poster on a classroom wall, every textbook illustration, every artist's rendering in a documentary is an educated guess, a reconstruction, a model based on limited observations of a structure we're trapped inside. We can map the positions of stars and gas clouds within a few thousand light years of the sun. We can measure distances and velocities. We can identify spiral arms by looking for concentrations of young stars. We can observe the galactic center in infrared light. We can detect hydrogen gas in radio wavelengths and trace its distribution across the galaxy. But we can't see the big picture. We can't step back and observe the overall structure. We're like ants crawling on the surface of a sculpture, able to measure the texture and contours of the surface near us, but unable to perceive the sculpture's overall form. Every map of the Milky Way is a reconstruction, assembled from fragmentary observations and theoretical models. Different reconstructions don't always agree. Some show 2 major spiral arms, others show 4. Some depict a massive bar, others a more modest one. The details vary depending on which data you emphasize and which models you trust.
And we can't leave. Not yet. Maybe not ever.
The nearest star is 4.2 light-years away. With our current technology, it would take tens of thousands of years to send a probe there. The edge of the galaxy is 50,000 light-years away. Even traveling at the speed of light, impossible with any physics we understand, it would take 50,000 years to reach a vantage point where you could see the Milky Way from the side. And to get a view from above, to see the spiral structure clearly, you'd need to travel hundreds of thousands of light-years, well beyond the galactic disk.
The Voyager 1 spacecraft, launched in 1977 and now the most distant human-made object, is about 24 billion kilometers from Earth, roughly 160 astronomical units, or 0.0026 light-years. At its current speed, it would take Voyager about 1,600 years to travel 1 light-year. To reach the nearest star would take about 73,000 years. To reach the edge of the galaxy would take roughly 2 billion years.
We're not leaving anytime soon. We're trapped inside the very thing we're trying to understand, limited by our position, our perspective, and the fundamental constraints of physics. And that means there's a limit to what we can know. No matter how advanced our telescopes become, no matter how sophisticated our simulations, no matter how much data we collect, there will always be uncertainty. There will always be gaps in our knowledge. There will always be mysteries that remain unsolved.
The Milky Way is home. It's the cosmic structure that gave birth to our solar system, that contains every star we can see with the naked eye, that defines the night sky, and has inspired wonder in every human who has ever looked up.
But it's also the ultimate puzzle, one we may be solving for centuries or millennia to come. And perhaps that's exactly as it should be. Perhaps the universe should contain mysteries that resist easy answers, phenomena that challenge our understanding, questions that keep us searching.
Perhaps the journey matters more than the destination. For most of human history, we didn't know we lived in a galaxy.
Our ancestors looked up at the Milky Way, that faint band of light stretching across the sky, and invented stories to explain it. In Greek mythology, it was milk spilled from the breast of the goddess Hera. In Hindu mythology, it was the celestial river Ganges flowing through the heavens. In Norse mythology, it was the path to Valhalla. Aboriginal Australians saw it as a river in the sky, or as smoke from campfires.
These weren't stupid explanations. They were attempts to make sense of a mysterious phenomenon using the conceptual frameworks available at the time. Our ancestors didn't have telescopes, didn't understand stars, didn't know about the vastness of space. They did the best they could with what they knew. The first person to realize the Milky Way was composed of stars was Galileo Galilei in 1610. When he pointed his primitive telescope, really just 2 lenses in a tube, at the Milky Way, he saw that the faint band of light resolved into countless individual stars, too numerous to count. This was revolutionary. It meant the Milky Way wasn't some celestial milk or river or path. It was a concentration of stars, vastly more than could be seen with the naked eye. But Galileo didn't know what this meant. He didn't know how those stars were arranged, or why they formed a band across the sky, or whether the sun was part of the structure or separate from it. For the next 3 centuries, astronomers debated the nature of the Milky Way and the universe beyond. Was the Milky Way the entire universe, containing all stars that existed? Or were there other structures beyond it, other island universes, as philosopher Immanuel Kant called them in 1755? The debate was complicated by a lack of distance measurements. Astronomers could see spiral nebulae, fuzzy patches of light that telescopes revealed had spiral structure, but they didn't know how far away these objects were. If they were small and nearby, they might be gas clouds within the Milky Way. If they were large and distant, they might be separate galaxies. The Great Debate of 1920, held at the Smithsonian in Washington, D.C., brought this question to the forefront. Astronomers Harlow Shapley and Heber Curtis presented arguments on opposite sides of the question. Was the Milky Way the entire universe, or was it just one of many galaxies? Shapley argued that spiral nebulae were within the Milky Way, making our galaxy the entirety of the observable universe.
Curtis argued that spiral nebulae were separate galaxies, island universes, far beyond the Milky Way.
The debate was settled in 1924 when Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory, measured the distance to the Andromeda Nebula using Cepheid variable stars, stars whose brightness varies regularly, with a period related to their intrinsic luminosity. By measuring the period and apparent brightness of Cepheids in Andromeda, Hubble calculated that Andromeda was roughly 900,000 light-years away. Later measurements revised this to 2.5 million light-years.
This was far beyond any plausible size for the Milky Way. Andromeda had to be a separate galaxy.
The universe suddenly got much larger. The Milky Way wasn't everything. It was just one galaxy among countless others.
But we still didn't know what the Milky Way looked like. We knew we lived in a galaxy, but we didn't know its structure.
In the 1950s and 1960s, radio astronomy revolutionized our understanding. Radio telescopes could detect the 21-centimeter emission line of neutral hydrogen, light with a wavelength of 21 centimeters produced when hydrogen atoms flip their electron spins. This radio emission passes through dust easily, allowing astronomers to map hydrogen gas throughout the galaxy.
By measuring the Doppler shifts of this emission, how the frequency changed due to motion toward or away from us, astronomers could determine the velocities of gas clouds and reconstruct their positions in 3 dimensions. The result was the first maps showing the Milky Way's spiral structure. We couldn't see it directly, but we could infer it from the distribution and motion of gas clouds.
In the following decades, infrared astronomy added more detail. Infrared telescopes launched into space, IRAS in 1983, ISO in 1995, Spitzer in 2003, mapped the galaxy in infrared light, revealing cool stars and dust that were invisible to optical telescopes.
The Hipparcos satellite, launched in 1989, measured accurate distances to over 100,000 stars using parallax, building the first detailed 3-dimensional map of the solar neighborhood.
And then came Gaia, launched in 2013, which has measured over 1.8 billion stars with unprecedented precision, creating the most detailed map of the Milky Way ever made. Each generation of instruments has revealed more detail, answered more questions, and raised new mysteries. We've gone from not knowing we lived in a galaxy to mapping billions of stars in 3 dimensions. From thinking the Milky Way was the entire universe to understanding it's one of hundreds of billions of galaxies. From seeing the Milky Way as a static structure to understanding it's dynamic, evolving, constantly consuming smaller galaxies and heading toward a collision with Andromeda. Our understanding has grown exponentially, but so has our awareness of how much we don't know. This is the paradox of scientific progress. The more we learn, the more we realize how little we know. Every answer opens new questions. Every observation reveals new phenomena we didn't expect. The frontier of knowledge doesn't shrink, it expands.
And this is cause for wonder, not despair. It means there will always be more to discover. There will always be mysteries to solve. There will always be a reason to keep looking up, keep asking questions, keep searching for understanding.
We are the first humans to know we live in a galaxy, the first to map its structure, the first to understand its history and predict its future, the first to realize we're not at the center of anything, not at the center of the solar system, not at the center of the galaxy, not at the center of the universe.
This knowledge is humbling, but it's also empowering, because understanding our cosmic context, understanding that we're part of something vast and ancient, gives us perspective on our place in the universe and our significance in the grand scheme of things.
We are small, individually, cosmically insignificant, tiny biological organisms on a small planet orbiting an ordinary star in the suburbs of an average galaxy.
But collectively, we're part of something extraordinary. We're the way the universe has become conscious of itself. We're matter that has organized itself in such a way that it can contemplate its own origins and wonder about its place in the cosmos.
We're the Milky Way, looking at itself, trying to understand itself. And that's remarkable. On a clear, dark night,
Far from city lights, you can see about 5,000 to 6,000 stars with the naked eye, depending on your eyesight and the darkness of the sky. Every single one of those stars is part of the Milky Way. In fact, every star you can see without a telescope is in the Milky Way, most within just a few hundred light years of Earth. The farthest star visible to the naked eye is V762 Cas in the constellation Cassiopeia, a variable star approximately 16,000 light-years away. At its brightest, it just barely reaches magnitude 5.8 at the limit of human vision. But most stars you see are much closer, within 1,000 light-years, many within just 100 light-years.
The brightest star in the night sky is Sirius in the constellation Canis Major. Sirius is only 8.6 light-years away, making it one of our closest neighbors. It's intrinsically very bright, about 25 times more luminous than the Sun, but its apparent brightness is due mostly to its proximity.
Other bright stars are farther away, but intrinsically more luminous. Rigel, in Orion, is about 860 light-years away, and roughly 120,000 times more luminous than the Sun. Deneb, in Cygnus, is approximately 2,600 light-years away, and perhaps 200,000 times more luminous than the Sun, one of the most intrinsically bright stars visible to the naked eye. These luminous stars are massive, hot, and short-lived. They burn through their fuel quickly, living only a few million years before exploding as supernovae. By contrast, the Sun will live about 10 billion years, and the smallest red dwarf stars can live for trillions of years. When you look at the night sky, you're seeing a biased sample of the galaxy. You're seeing mostly bright, massive stars that are intrinsically luminous enough to be visible across hundreds or thousands of light-years. You're not seeing the faint red dwarfs that make up the majority of stars in the galaxy. They're too dim to see without telescopes, unless they're very close to us.
The Milky Way itself, the faint band of light stretching across the sky, is visible on dark nights, though increasingly few people have seen it due to light pollution. About 80% of people in North America and Europe live under skies so bright that the Milky Way is invisible.
This is a tragedy. For all of human history, until the last century or so, everyone who looked up on a clear night could see the Milky Way. It was part of the human experience, part of our connection to the cosmos. Now, for most people, it's gone, washed out by artificial light.
But in dark locations, national parks, deserts, remote islands, the Milky Way is spectacular. It stretches from horizon to horizon, a river of light studded with dark lanes of dust, bright patches of nebulae, and dense star clouds near the galactic center.
What you're seeing when you look at the Milky Way is the combined light of billions of stars, too distant and too faint to see individually. You're looking edge-on through the galactic disk, through the spiral arms, through concentrations of stars and gas that extend for thousands of light-years.
The brightest part of the Milky Way, visible from the southern hemisphere or low northern latitudes, is toward the galactic center in the constellation Sagittarius. This region is packed with stars, so dense that even though the galactic center is 26,000 light-years away, the combined light of all those stars makes this region appear brighter than any other part of the Milky Way.
The dark lanes you see in the Milky Way aren't empty space, they're clouds of dust blocking the light from more distant stars. The most prominent dark lane is called the Great Rift, running through Cygnus and Aquila, a vast cloud of dust that obscures part of the galactic disk.
With binoculars or a small telescope, the Milky Way transforms. Regions that appear as faint smudges to the naked eye resolve into thousands of individual stars. Star clusters become visible, dense concentrations of stars born together, still orbiting close to each other. The Pleiades, or Seven Sisters, is an open cluster in Taurus, about 440 light-years away, containing hundreds of young, hot stars. To the naked eye, you can see 6 or 7 stars. With binoculars, you see dozens. With a telescope, hundreds. The Beehive cluster in Cancer, the Double cluster in Perseus, the Wild Duck cluster in Scutum. These are just a few of the many star clusters visible with small telescopes. Each one a family of stars born from the same molecular cloud, now slowly drifting apart as they orbit the galaxy. Globular clusters are even more impressive. These dense spheres of ancient stars, orbiting in the galactic halo, contain hundreds of thousands or millions of stars packed into regions only a few dozen light-years across.
The most spectacular globular cluster visible from the northern hemisphere is M13, the Great Globular Cluster in Hercules, about 25,000 light-years away. With a telescope, it appears as a dense ball of stars, so tightly packed toward the center that individual stars can't be resolved. They blend into a glowing core.
From the southern hemisphere, Omega Centauri is even more spectacular, the largest globular cluster associated with the Milky Way, containing about 10 million stars, visible to the naked eye as a faint, fuzzy star.
Nebulae, clouds of gas and dust, are some of the most beautiful objects in the night sky. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is a stellar nursery about 1,340 light-years away, where new stars are being born right now. Through a telescope, it reveals intricate structure: glowing gas, dark dust lanes, bright young stars illuminating the surrounding material. The Lagoon Nebula, the Trifid Nebula, the Eagle Nebula. These are just a few of the nebulae visible from Earth, each one a glimpse of the ongoing process of star formation happening throughout the galaxy.
And then there are the planetary nebulae. Misleadingly named, they're not related to planets at all, but are shells of gas ejected by dying stars. The Ring Nebula in Lyra, the Dumbbell Nebula in Vulpecula, the Cat's Eye Nebula in Draco. Each is the death shroud of a star that exhausted its fuel and blew off its outer layers, leaving behind a hot white dwarf core surrounded by an expanding shell of glowing gas.
Everything you can see in the night sky, every star, every cluster, every nebula, every object visible through backyard telescopes is part of the Milky Way. We're embedded in it, surrounded by it, part of it. The night sky isn't something separate from us, something we observe from the outside. It's our neighborhood, our cosmic home, the structure we inhabit.
And the more you learn about what you're seeing, the distances, the ages, the life cycles of stars, the more magnificent it becomes.
The Milky Way isn't static, it's alive in a sense, constantly changing, evolving, cycling matter through stellar life cycles that have been ongoing for billions of years. Stars are born in molecular clouds, vast regions of cold gas and dust where densities are high enough for gravity to overcome thermal pressure and pull material together. These clouds are enormous, hundreds or thousands of times more massive than the Sun, spanning tens or hundreds of light years. Inside these clouds, denser regions collapse under their own gravity, fragmenting into smaller clumps. Each clump continues to collapse, heating up as gravitational potential energy converts to thermal energy. Eventually, the core becomes hot enough, about 10 million degrees Celsius, for nuclear fusion to begin. Hydrogen atoms fuse into helium, releasing enormous amounts of energy. A star is born. The newly formed star emerges from its cocoon of gas and dust, its stellar winds and radiation blowing away the surrounding material, revealing a young solar system that might include planets, asteroids, comets, and all the other components we see in our own solar system. The star then enters the main sequence, the stable phase of stellar life where it fuses hydrogen into helium in its core. Our Sun is currently in this phase, has been for about 4.6 billion years, and will continue for another 5 billion years or so. How long a star remains on the main sequence depends on its mass. Massive stars burn through their fuel quickly. A star 10 times the mass of the Sun might last only 20 million years. A star like the Sun lasts about 10 billion years. Small red dwarf stars with masses less than half the Sun's can last for trillions of years, longer than the current age of the universe. Eventually, every star exhausts the hydrogen in its core. What happens next depends on the star's mass. For stars like the Sun, the core contracts and heats up, while the outer layers expand enormously. The star becomes a red giant, hundreds of times larger than its main sequence size. The Sun will eventually expand to perhaps 100 or 200 times its current radius, possibly reaching Earth's orbit. In the red giant phase, the star begins fusing helium into carbon and oxygen in its core,
generating a second lease on life. But this phase is brief, only a few 100 million years for a star like the Sun.
Eventually, helium fusion ceases. The core collapses into a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen, no longer undergoing fusion, gradually cooling over billions of years. The outer layers are blown off, forming a planetary nebula, a beautiful, short-lived shell of glowing gas expanding into space.
White dwarfs can last almost forever, slowly cooling and fading into black dwarfs, cold, dark stellar corpses. But the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs are still glowing faintly with residual heat from their formation.
For massive stars, those with more than about 8 times the Sun's mass, the end is more dramatic.
These stars fuse heavier and heavier elements in their cores: helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each stage is shorter than the last. A massive star might spend millions of years fusing hydrogen, a few 100,000 years fusing helium, 1,000 years fusing carbon, a few years fusing silicon.
But iron is the end of the line. Fusing iron doesn't release energy, it absorbs energy. Once the core becomes iron, fusion stops. The core is no longer supported by the pressure of nuclear fusion. Gravity wins. The core collapses catastrophically in less than a second, falling inward until the density becomes so high that electrons and protons are forced together, forming neutrons. The collapse halts suddenly when the core reaches nuclear density, creating a shock wave that propagates outward through the star. This shock wave blows the star apart in a supernova explosion, one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy, releasing as much energy as the Sun will produce in its entire 10 billion year lifetime. The explosion scatters heavy elements into space. All the elements heavier than iron are created in supernovae or in the collisions of neutron stars. Every atom of gold, silver, platinum, uranium, every element that can't be produced by normal stellar fusion, was created in these violent events and scattered across the galaxy.
These heavy elements mix with the interstellar medium, enriching it, increasing its metallicity, the fraction of elements heavier than hydrogen and helium. The next generation of stars that forms from this enriched gas will contain more heavy elements, and their planets will too.
This is why the existence of Earth is directly tied to the deaths of ancient stars. The oxygen you breathe, the carbon in your body, the iron in your blood, the calcium in your bones, all of it was forged inside stars that exploded billions of years ago, long before the Sun existed.
You are made of stardust, literally. Every atom in your body, except for hydrogen, was created inside a star or in a stellar explosion, then scattered into space, eventually incorporated into the molecular cloud that collapsed to form the solar system 4.6 billion years ago.
The core left behind by a supernova becomes either a neutron star or a black hole, depending on the original star's mass. Neutron stars are the densest objects in the universe, aside from black holes, objects with roughly the Sun's mass compressed into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons on Earth.
Neutron stars often rotate rapidly, sometimes hundreds of times per second. And if their magnetic fields are oriented correctly, they emit beams of radiation from their poles. As the star rotates, these beams sweep across space like a lighthouse, and if they happen to sweep past Earth, we detect them as pulsars, rhythmic pulses of radio emission arriving with clockwork precision.
The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who initially thought the regular pulses might be signals from an extraterrestrial civilization. She jokingly called the source LGM-1 for Little Green Men. But further observations revealed pulsars were natural phenomena, rapidly rotating neutron stars.
For the most massive stars, those with initial masses above about 20 to 25 solar masses, even a neutron star can't support the remnant core. Gravity overwhelms all opposing forces, and the core collapses into a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape.
These stellar mass black holes, ranging from a few solar masses to perhaps 100 solar masses, are scattered throughout the galaxy. We can't see them directly, but we can detect them when they're part of binary systems, pulling material off a companion star. The infalling material heats up to millions of degrees and emits X-rays before crossing the event horizon and disappearing forever. The galaxy contains millions of stellar mass black holes, most of them invisible, isolated objects drifting through space. Every massive star that has ever exploded left behind either a neutron star or a black hole, and over billions of years, that adds up to an enormous population.
This cycle, star birth, life, death, and rebirth, has been ongoing for most of the galaxy's history. The first stars, formed from pristine gas containing only hydrogen and helium from the Big Bang, lived and died, enriching the interstellar medium with heavy elements. The second generation of stars, formed from this enriched gas, lived and died, enriching it further. And so on, generation after generation, each one containing more heavy elements than the last.
The Sun is a third-generation star, maybe fourth generation. It contains about 2% heavy elements by mass, the product of billions of years of stellar nucleosynthesis and supernovae. The first stars contained essentially zero heavy elements. They were pure hydrogen and helium. This enrichment process is crucial for life. Rocky planets like Earth can't form without heavy elements. You need carbon, oxygen, silicon, iron, magnesium. Gas clouds made purely of hydrogen and helium can produce only gas giant planets, like Jupiter. Life as we know it requires heavy elements. Carbon-based chemistry, liquid water, complex molecules, all of it depends on elements that didn't exist in the early universe and had to be created inside stars. So when we say we're made of stardust, we're not being poetic. We're stating a literal fact about cosmic evolution. The galaxy has been recycling material through stellar life cycles for billions of years, gradually building up the chemical complexity necessary for planets and life.
And this process continues. Right now, in molecular clouds throughout the galaxy, new stars are being born. In a few million or billion years, some of those stars will die, enriching the interstellar medium further, and the cycle will continue.
The Milky Way is a cosmic recycling plant, transforming hydrogen into heavier elements, generation after generation, slowly increasing the chemical complexity of the universe.
And we're part of that process. When the Sun dies, it will return most of its mass to the interstellar medium. The atoms that make up Earth, including the atoms in your body, will eventually be dispersed into space, where they might be incorporated into future stars and planets.
In a sense, we're temporary arrangements of matter, borrowed from the galaxy for a brief time, destined to return to the cosmic cycle when our time is done.
The Milky Way is not unique. It's one of hundreds of billions of galaxies in the observable universe, maybe as many as 2 trillion galaxies, each containing billions or hundreds of billions of stars.
But how does our galaxy compare to others? In terms of size and mass, the Milky Way is large, but not exceptionally so. It's classified as a large spiral galaxy, but there are bigger ones. The Andromeda galaxy is somewhat larger, containing perhaps 1 trillion stars, compared to the Milky Way's few hundred billion. The galaxy IC 1101, an enormous elliptical galaxy about 1 billion light-years away, is one of the largest known galaxies, containing perhaps 100 trillion stars and spanning about 6 million light-years, 60 times larger than the Milky Way. At the other end of the scale, there are dwarf galaxies containing only millions or billions of stars. The Sagittarius dwarf elliptical galaxy, currently being consumed by the Milky Way, contains only about 4 billion stars. The Segway 2 dwarf galaxy, one of the smallest known galaxies, contains only about 1,000 stars. You could almost count them individually if you had a good enough telescope. The Milky Way sits somewhere in the middle of the galactic mass distribution. It's bigger than most galaxies. Most galaxies in the universe are small dwarfs, but it's not among the giants. In terms of structure, the Milky Way is a barred spiral galaxy, a common type representing perhaps 60–70% of all spiral galaxies. The bar and spiral arms are normal features, seen in countless other galaxies throughout the universe. But there are other types of galaxies too.
Elliptical galaxies, ranging from small dwarf ellipticals to enormous giants, contain mostly old stars and very little gas. They've already used up most of their star-forming material. Irregular galaxies have no clear structure, no spiral arms or central bulge, just chaotic distributions of stars and gas. Lenticular galaxies are intermediate between spirals and ellipticals, with a disk but no spiral arms.
The Milky Way's star formation rate, about 1 to 3 solar masses of new stars per year, is fairly typical for a galaxy of its size and type. Some galaxies are much more active, forming hundreds or even thousands of solar masses of new stars per year. These starburst galaxies are often the result of collisions or mergers, where gas clouds are compressed and triggered into rapid star formation.
Other galaxies are quiescent, forming very few new stars, having exhausted most of their gas or had it stripped away by interactions with other galaxies or the intergalactic medium. The Milky Way is moderately active, not a starburst, but not quiescent either. It's forming new stars at a steady, sustainable rate, typical of spiral galaxies in the current universe. One unusual feature of the Milky Way is its satellite system. Most large galaxies have satellite galaxies orbiting them, smaller galaxies captured by gravity, unable to escape. The Milky Way has dozens of known satellites, including the Magellanic Clouds, the Sagittarius Dwarf Elliptical Galaxy, and numerous ultra-faint dwarfs containing only thousands to millions of stars. But theoretical models predict there should be more satellites than we observe. Hundreds, perhaps thousands of small dark matter halos orbiting the Milky Way, each potentially hosting a tiny dwarf galaxy. This discrepancy between predicted and observed numbers of satellites is called the missing satellites problem and remains unsolved. Either the models are wrong, or many satellite galaxies are so faint we haven't detected them yet, or the process of galaxy formation is more complex than we understand. The Milky Way also appears to have a relatively quiet recent history compared to some galaxies. It hasn't experienced a major merger, a collision with a galaxy of comparable size, for several billion years. The merger with Gaia Enceladus happened 8 to 11 billion years ago, and since then, the Milky Way has consumed only smaller dwarf galaxies. Some galaxies show evidence of much more recent major mergers, with distorted structures, tidal tails, and irregular morphologies. The galaxy NGC 4038/4039, known as the Antennae galaxies, is currently undergoing a major merger, its two progenitor galaxies completely disrupted and producing long tidal tails visible even in amateur telescopes. The Milky Way's relatively quiet history might be important for life. Major mergers trigger intense star formation, which produces many massive stars, which explode as supernovae, potentially sterilizing large regions of galaxies with radiation. A quiet galactic history might be necessary for complex life to evolve. But we don't know if this is actually true. We have only one example of a galaxy with known complex life, our own, and we don't know whether the Milky Way's properties are typical or unusual in this regard. One thing we do know, the Milky Way is part of the Local Group, a small cluster of about 80 known galaxies gravitationally bound together. The Local Group is dominated by 3 large spirals, the Milky Way, Andromeda, and Triangulum, plus dozens of smaller dwarf galaxies. Most galaxies exist in groups or clusters. Some clusters are enormous, containing thousands of galaxies. The Virgo cluster, about 65 million light-years away, contains more than 1,500 galaxies. The Coma cluster, about 320 million light-years away, contains more than 1,000 large galaxies plus thousands of smaller ones. The Local Group is small by comparison, containing only 80 known members, most of them tiny dwarfs. But it's gravitationally bound. All the galaxies in the Local Group orbit their common center of mass, held together by gravity, slowly interacting and occasionally colliding. In the larger cosmic structure, the Local Group is part of the Virgo supercluster, an enormous structure containing about 100 galaxy groups and clusters, spread across about 110 million light-years. The Virgo supercluster contains roughly 47,000 galaxies, including the Milky Way. And the Virgo supercluster itself is part of an even larger structure called Laniakea, a gravitationally bound supercluster of superclusters containing about 100,000 galaxies across 520 million light-years.
These structures, galaxy groups, clusters, superclusters, form a cosmic web, with galaxies arranged in filaments and sheets surrounding vast empty voids. This web structure is shaped primarily by dark matter, whose gravity pulled galaxies together into these patterns over billions of years.
The Milky Way is just one node in this enormous cosmic web, a typical large spiral galaxy in a small group, part of a larger supercluster, part of the vast structure of the universe.
In this context, the Milky Way is both ordinary and extraordinary. Ordinary because it's similar to countless other galaxies, a barred spiral, moderate size, moderate star formation rate, typical structure. But extraordinary because it's our home, the only galaxy we can study in detail, the only galaxy we know contains life.
And that makes it special, regardless of how typical or atypical it might be in other respects. Let's return to where we started, with a question that should make you feel small and significant at the same time. Everything you've ever known exists inside a structure we've never seen from the outside. You've spent your entire life, every moment, every experience, every memory, inside the Milky Way. So has every human who came before you. So will every human who comes after, at least for the foreseeable future, and likely for all of human history. We are galactic natives, born in a specific spiral arm of a specific barred spiral galaxy at a specific moment in cosmic history, approximately 13.6 billion years after the galaxy formed, in the final third of the universe's current age. And yet, despite living here, despite being embedded in the galaxy's structure, despite being made literally of material the galaxy has recycled through stellar life cycles, we barely understand it.
We can't see the whole thing, we can't map it completely, we don't know what most of it is made of. We're only beginning to understand its past, and its future is a projection based on incomplete data and uncertain models.
But maybe that's exactly as it should be. Maybe the Milky Way isn't supposed to be fully understood, at least not yet. Maybe it's too vast, too complex, too dynamic for any inhabitants, no matter how intelligent or advanced, to comprehend completely from the inside. Or maybe we're just at the beginning of a process that will take centuries or millennia. Maybe 1,000 years from now, humans or whatever we evolve into will look back at this moment and marvel at how little we knew. Maybe they'll have mapped every star, measured every velocity, solved the mystery of dark matter, and understood the galaxy in ways we can't currently imagine. But I doubt it. Not because we're incapable of understanding, but because the more we learn, the more questions we discover. Every answer opens new mysteries, every observation reveals new complexity, every solution creates new puzzles. The Milky Way is a problem that gets bigger the more we learn about it, a mystery that deepens even as we peel back its layers. And that's not a failure. It's not a source of frustration. It's a gift. Because it means there's always more to discover. There's always something we don't understand. There's always a reason to keep looking up, to keep asking questions, to keep pushing the boundaries of human knowledge.
We live inside a galaxy of 100 billion stars, maybe 400 billion, maybe more. A galaxy that's colliding with other galaxies, held together by invisible matter, spinning through space at hundreds of kilometers per second. Part of a larger cosmic web stretching across billions of light years.
We live inside a cosmic island we'll never fully see, surrounded by mysteries we may never completely solve, embedded in structures we can barely perceive. And yet, we keep trying. We build telescopes, we launch spacecraft, we make measurements, construct theories, test predictions. We map the unmappable, chart the unchartable, trying to understand the structure we're trapped inside. Not because we need to, not because it's practical or profitable, not because it will extend our lives or make us wealthy or solve immediate problems, but because we're curious, because we want to know,
Because we're driven by the same impulse that made early humans look up at the Milky Way stretched across the night sky and wonder what it was, where it came from, whether it had meaning. We are a species that asks questions. It's arguably our defining characteristic. We don't just accept the world as it is. We probe it, test it, try to understand it. We want to know not just how things work, but why. Not just what exists, but where it came from and where it's going.
This drive, this curiosity, this need to understand is what makes us human. It's what led us from wondering about the band of light in the sky to mapping billions of stars in 3 dimensions. From thinking Earth was the center of everything to understanding we're a tiny speck in an incomprehensibly vast structure. Every step of that journey required someone to ask a question, to notice something strange, to propose an explanation, to test it, to build instruments that could see farther and measure more precisely. The Milky Way is an answer to questions humans have been asking for millennia, but it's an answer that keeps evolving, keeps growing more complex, keeps revealing new depths. And that's beautiful.
So, the next time you look up at the night sky, if you're lucky enough to be somewhere dark enough to see the Milky Way, remember this.
You're not looking at the Milky Way, you're looking through it. Those stars, those distant points of light, are your neighbors in a structure so vast that light takes 100,000 years to cross it. You share this galaxy with them. You're orbiting the same black hole, following the same gravitational currents, participating in the same cosmic dance.
You are not separate from the Milky Way. You are part of it.
Every atom in your body was forged in a star, somewhere in this galaxy or another, billions of years ago. The calcium in your bones came from a supernova. The iron in your blood was created inside a massive star and scattered into space when that star exploded. The oxygen you breathe, the carbon in your DNA, the nitrogen in your proteins, all of it came from stellar nucleosynthesis, the process by which stars create heavier elements from lighter ones. You are made of the galaxy. You are stardust, organized in a particular way for a brief time, conscious and aware, able to look up and contemplate your own origins. And the galaxy is made of countless beings like you, or if not exactly like you, then at least beings who might look up at their own night sky and ask similar questions. Beings who might wonder where they came from, why they exist, whether they're alone. We don't know if we're alone in the Milky Way. We don't know if life is common or rare, whether intelligence is typical or extraordinary, whether technological civilizations like ours exist elsewhere, or if we're the only ones. But statistically, given the number of stars and planets, it seems unlikely we're alone. Somewhere out there, in some other spiral arm, orbiting some other star, there might be someone else looking up at the same galaxy from a different perspective, asking the same questions. Or maybe not. Maybe we are alone. Maybe Earth is special, unique, the only place in the entire galaxy, perhaps the entire universe, where matter has organized itself into conscious, questioning beings. Either answer is profound. Either we're part of a galaxy teeming with life, or we're a cosmic miracle, unimaginably rare. Both possibilities should inspire wonder. We live inside something immense, ancient, and beautiful. Something that existed for 13 billion years before we appeared, and will continue existing for trillions of years after we're gone. Something we'll spend lifetimes trying to understand, and probably never fully succeed. And maybe, just maybe, that's exactly where we're supposed to be. Not at the center of anything, not special in any cosmic sense, not chosen or privileged or significant on galactic scales. Just participants in an ongoing cosmic story, matter that has become conscious and curious, atoms that have organized themselves into beings capable of wonder. The Milky Way doesn't care that we exist. It doesn't know we're here. It will continue spinning, evolving, colliding with Andromeda, recycling matter through stellar life cycles, regardless of whether humans survive or perish.
But we care. We notice. We wonder. We ask questions and search for answers.
And in that sense, we are significant. Not because the universe cares about us,
but because we care about the universe. Not because we're important on cosmic scales, but because we can contemplate cosmic scales and find meaning in them.
The Milky Way is home. It's the structure that birthed our solar system, that contains every star we can see with our eyes, that defines our cosmic neighborhood and our place in the universe.
It's also a mystery, a puzzle, a frontier that will keep humans occupied for as long as we exist.
And that's a gift, because it means the story isn't over. We haven't learned everything. We haven't answered all the questions. There's more to discover, more to understand, more to wonder about.
The Milky Way stretches overhead, a river of light spanning the sky, beautiful and mysterious, familiar yet incomprehensible. It's been there every night of your life, whether you noticed it or not. It will be there every night for the rest of your life, and for countless generations to come.
It's home, and it's still full of secrets.
That's the paradox of the Milky Way. It's simultaneously the most familiar structure in the universe, our home, the galaxy we live inside, and one of the most mysterious, full of unknowns and unanswered questions.
We know we live here. We know its approximate size, structure, and composition. We know its history and can predict its future. We've mapped billions of its stars and studied its processes in extraordinary detail. And yet, we've never seen it from outside. We don't know what most of it is made of. We can't explain many of its properties or predict its evolution with certainty. We're inside a structure we're trying to understand, using instruments and methods that themselves are part of that structure, limited by our perspective and our position. It's like being inside a giant machine, trying to figure out how it works by examining the parts you can reach, making measurements, building models, testing predictions. You might eventually understand quite a lot, but some aspects will always remain obscure, hidden, accessible only through inference and theory. That's the human condition, cosmically speaking. We're inside the Milky Way, trying to understand it from the inside, with all the limitations that imposes.
But we keep trying, and that persistence, that curiosity, that refusal to accept ignorance when understanding might be possible, that's what makes us remarkable.
Not because we've succeeded in understanding everything, but because we keep trying, despite the obstacles, despite the limitations, despite knowing that complete understanding might be impossible.
We are the Milky Way, becoming conscious of itself. Matter that has organized itself in such a way that it can contemplate its own origins, trace its own history, predict its own future.
And if that's not miraculous, nothing is.
So look up, notice the stars. Remember that you're part of this structure, this vast cosmic island spinning through space. Remember that every atom in your body came from the galaxy's recycling processes. Remember that you're temporary. Your atoms will return to the cosmic cycle eventually. But also significant, because you can wonder and question and search for meaning.
The Milky Way is vast. We are small, but we're conscious, curious, and capable of understanding, at least partially, the structure we inhabit. And that makes all the difference.
That's the story of the Milky Way. Not a complete story, never complete, always evolving, but our story. The story of humanity's attempt to understand its cosmic home. It's a story without an ending, a question without a final answer, a mystery that deepens even as we solve pieces of it.
And it's the greatest story we have, because it's real. Not mythology or fiction, but the actual history and structure of the universe we inhabit. We live inside a galaxy we barely understand, held together by forces we can't explain. Embedded in a cosmic web stretching across billions of light years. Part of a universe that might be infinite, that might contain countless other galaxies, and perhaps countless other civilizations, asking the same questions we ask. That's humbling. That's awe-inspiring. That's worth contemplating.
Because in the end, understanding the Milky Way isn't just about astronomy or astrophysics or cosmology. It's about understanding ourselves, where we came from, why we're here, what our place is in the vast cosmic structure.
And those are questions worth asking, even if we never find complete answers.
especially if we never find complete answers.
Because the search itself, the process of questioning, observing, theorizing, testing, is what makes us human.
The Milky Way is our home, our birthplace, our cosmic context, the structure that defines our existence and shapes our destiny.
And it's still full of secrets, still waiting to be explored, still offering new mysteries for future generations to solve.
That's the gift of living inside something too vast to fully comprehend. There's always more to discover, always another question to ask, always another mystery waiting just beyond our current understanding.
The Milky Way explained, except it isn't. Not fully, not yet, perhaps never completely.
And that's exactly as it should be.